let's get started. So the plan for today is that I have one example I prepared. I want to go over that. After that, we can look at those two homework problems that people were interested in earlier sections, number 4 and number 5. So maybe we can spend some time on those to at least help you get started. But do you have any questions from looking at the homework problems? Okay. All right, let's just jump into let's get this started. So the example I have is we're going to solve this initial value problem, 2y double prime plus 3y prime minus 2y equals t e to the negative 2t with initial conditions y of 0 equals y prime of 0 equals 0. So both initial conditions are 0. And I want to go through this because this example, the right-hand side, it's a function of t and e to the at. It's a little bit complicated. We got to use the special rule you learned recently, the S translation. So let me write down that on the side. So S translation. Which says that if we find the Laplace transform of e to the at f of t, what we could try to do is that we could just kind of take the e to the at outside, like ignore it for a while, just finding the Laplace transform of f of t first. After we found the Laplace transform of f of t, we're going to replace the s in that final answer there with s minus a. So that will give us a Laplace transform of e to the at f of t. So you can think about this as a sort of a shortcut. So the first step is ignore this for a while, and then at the end, to compensate for that part that we ignored, we're going to replace s with s minus a. And this technique works well when we use the inverse Laplace transform. So if we have inverse Laplace of some function f of s with s goes to s minus a, for example, what we could do is that when we find the inverse, we could just take this notation and put it aside, not worry about it. By putting this translation here, consider that equivalent to e to the at. So we can just focus on inverse Laplace transform of f of s. And then at the end, we're going to multiply with e to the at, which is corresponding to this translation. So that's what we're going to use at some point in this example. Let me begin with taking the example and find the Laplace transform of every term. I'm going to skip some details there, so that will be 2 Laplace transform of y double prime plus 3 Laplace transform of y prime minus 2 Laplace transform of y, and then that's equal to Laplace transform of t e to the negative 2t. That's the beginning step. From here, I'm going to substitute for the Laplace transform of the 3 terms on the left. So that will give us 2 brackets s squared capital Y of s minus s times lowercase y of 0 minus lowercase y of 0 derivative, the y prime of 0. I'm going to move it down a little bit, running out of space there. And I'm going to plus 3 times s capital Y of s minus y lowercase y of 0. So that's the Laplace transform of y prime, and then minus 2 times capital Y of s. That's the left-hand side. The right-hand side, so here we have a t and also e to the negative 2t. So we're going to extract e to the negative 2t and just ignore it for a while. It doesn't mean we get rid of it completely, just that we don't want it to be in the way for a brief moment. So we're going to find the Laplace transform of just t. And after we've done that, we're going to have to do the translation. So right now I'm going to just note that at the end, the s will be replaced with s minus a, so s minus negative 2. So this negative 2 coming from the negative 2 in the exponent of base e of the exponential part. Okay, so we know what the Laplace transform of t is, right? So that's just a 1 over s squared. But don't forget that we have this translation. S goes to s minus negative 2, so s plus 2. And in the next step, we're actually going to replace the s in the denominator with s plus 2. So 1 over s plus 2 squared. That's the right-hand side. Any questions about that translation? To find the Laplace transform of t e to the negative 2t. And obviously the left-hand side, now we can actually plug in all the numbers that we know. Well, just a couple of zeros we have to put in there. So that's a 0, that's a 0, that's a 0. And if we rewrite it with what we have left, we have 2s squared capital Y of s plus 3s capital Y of s minus 2y of s. That's the left-hand side. The right-hand side is just 1 over s plus 2 squared. So I'm going to solve for y of s by factoring it out first. So we get 2s squared plus 3s minus 2 times capital Y of s equals 1 over s plus 2 squared. And then I'm going to divide both sides by this parentheses on the left here. So we got capital Y of s equals 1 over, so what do we have? We have 2s squared plus 3s minus 2, and also we had s plus 2 squared. So we solved for Y of s. Okay, so we did a good amount of work. Now we can actually find out what the y of t is, right? Because this is the Laplace transform of y of t. We have to apply the inverse. But instead of stick this into the inverse Laplace transform notation all the time, what we could do is that we could look at this and think, okay, this is complicated. We probably have to use partial fractions at some point to find out the simple fractions. The simpler fraction there, and then find the inverse of Laplace transform. So what we're going to do is that we actually simplify this first before we apply the inverse Laplace transform. So to simplify, we have to factor the denominator. So it turns out that the first parentheses in the denominator can be factored nicely into. So we have 2s squared plus 3s minus 2, so if we want to factor that, that's become 2s and s. That will give us 2s squared. We also need two numbers multiplied to give us negative 2, so 1, negative 2, negative 2, 1. 1, negative 2, negative 1, so it doesn't matter, so you have to figure out which one goes where, right? Because we need 3s positive, so we need 2s times a positive 2. So we need a positive 2 there. And then on the left we have a negative 1 you can always double check. So this is minus s, this is positive 4s, give us positive 3s. Okay, so this is good because we could actually add combine the s plus 2 into one fraction. So it's the s plus 2, s plus 2 squared, so that's s plus 2 cubed. So this gives us 1 over, I'm going to put on the side here, 2s minus 1, s plus 2 cubed. From this point, we're going to find the partial fractions first before we apply the inverse Laplace transform. So find the partial fractions of this fraction. 1, I'm going to rewrite it 1 over 2s minus 1 s plus 2 cubed. And I'm going to just write down the 4 fractions that you should have when you find the partial fractions without doing a lot of work. The first one is the first one has a denominator 2s minus 1. It's a linear, so the numerator is just a. The second one has a denominator s plus 2, so the numerator will be b. The third one has a denominator s plus 2 squared, right? Because if we have s plus 2 cubed, the 3 factors s plus 2, when we find partial fractions, we have to use all 3 of them. So the first one is s plus 2, the second one is s plus 2 squared, because we could have just used s plus 2 again, because then it will be the same as the second one. So we just have to increase the exponent by 1 each time. And then we have s plus 2 cubed. The numerators are just constant c, d. You should be able to figure out a, b, c, d. It's not nice, but it's manageable. So a ends up to be 8 over 125. B is negative 4 over 125. C is negative 2 over 25. D is negative 1/5. Is it okay if I don't do any work to show how I derive this? Okay. To be honest, I did not derive it. I look it up. I don't know if you're familiar with this website. It's called Wolfram Alpha. I probably didn't spell it right. You probably use it before. I use it a lot. I just typed this. I said partial fractions of this fraction of that, and then they give me the partial fractions. And if you're good with other programs, I think a Maple also does the work. And I'm sure you also know other ones. Okay, so anyway, so that's what I did over there, and then now we can actually write down the partial fractions, which is, when I write down the partial fractions, I'm going to take the a, b, c, d on the side of the fractions, not in the numerator. So I get 8 over 125 times 1 over 2s minus 1 plus, it's minus 4 over 125 times 1 over s plus 2. This is just personal preference. You can definitely put it in the numerator if you want. So minus 2 over 25, 1 over s plus 2 squared, minus 1/5, 1 over s plus 2 cubed. And then we can just apply the inverse Laplace transformation to all of those to get y of t. And when we do that, we don't have to keep the constants inside, we can keep them outside, so that we have 8 over 125, inverse Laplace of 1 over 2s minus 1. Then we have minus 4 over 125 inverse Laplace of 1 over s plus 2. And then minus 2 over 25 inverse Laplace of 1 over s plus 2 squared. And then the last one is minus 1 over 5 inverse Laplace transform of 1 over s plus 2 cubed. Then we have to figure out each one of them. So if we just look at them, one of them is very straightforward. Because the denominator is s minus 8, well not exactly s minus 8, it's s plus 8, but you can treat it as minus negative 2, so this one is relatively easier. This one is pretty easy, but it's not exactly the form that we're familiar with. So the first term, so we want, let me list that, we want the denominator to be either going to be denominators to be either going to be just s minus a, s squared plus k squared. You know, if we have those, that'll be nice. If not, we can live with s minus a squared. If we don't have this one, maybe we can live with s minus a squared plus k squared. But don't worry about the last two. We want to have something like those first. It looks like this second term is good. Almost good. But the first term we have to do something, right? Because we have 2s instead of s. So that means we need to take out the 2. So we need to factor out 2 there from the denominator. So this becomes, if we just factor out a 2, so we get Laplace, inverse Laplace of 1 over 2 times s minus 1 half, if we factor out a 2 from the denominator. And that 1 half, well, the 1 over 2, we can actually put outside of the inverse. So that becomes 1 half inverse Laplace transform of 1 over s minus 1 half. Now this is good because this is the s minus a in the denominator. What about the middle term? Well, the middle term is, like I said, is pretty close. Even though we have s plus 2, we have seen this, we can just treat it as inverse Laplace of 1 over s minus a negative 2. There's not much manipulation we need to do, just one small manipulation there. Okay, what about the next one? The next one is s plus 2 squared. It's not the first three, but it looks like in this case. Okay, that's fine. So if we have something s minus a squared, we can actually apply the x translation by replacing s plus 2 with a new x. So this part, we can replace it with just a new s. So note that this becomes inverse Laplace of 1 over s squared. But this s here actually come from s plus 2. It's not just the s, it actually comes from s plus 2 being replaced with s. So what this tells us is that in the next step, this translation is going to give us an exponential part like we did at the beginning. So this will be e raised to the negative 2t. And this 1 over s inverse Laplace transformation will give us t. So from here, this is going to give us t for the first part, but then the s goes to s what? The s plus 2 being replaced with s, that translation will give us e to the negative 2t. Just like we did beginning, we kind of ignore e to the negative 2t. At the end, we write down s goes to s plus 2. Here, if we have s goes to s plus 2 as a substitution, then we have to keep in mind that that eventually tends into e to the negative 2t. Does that make sense? Okay. All right, let's look at the last part. Looks like the last one is similar to the one before. We can try to apply the same idea. That's correct. So let's apply the same concept there. This will become inverse of 1 over s cubed with the translation s coming from s goes to, s coming from s plus 2. And then this part we have to do a little bit extra work to figure out what the corresponding function is, but s goes to s plus 2 here eventually tends into e to the negative 2t like this one. So note that this eventually tends into e to the negative 2t, but the question is, what about this one? It's not in the table, but the table gives you something similar. Let me ask you, any questions before I talk about how to get this correct inverse Laplace transformation? All right, so from here, what we're going to do is that we want to know, I'm just going to write in the next line, so want to find the inverse Laplace of 1 over s cubed. It's not listed in the table, but from the table, we have this relationship. We have t to the n corresponding to n factorial over s to the n plus 1. That's what we know from the table. And this is the closest that we can use, because this is the s to a power in the denominator. This is the s to a power in the denominator. We're going to have to use this one. How do we use it correctly? You probably figured out already, but I just want to explain it just in case there's a little bit of confusion. So here we have 1 over s cubed. But in the table, I have a denominator s to the n plus 1, so I'm going to rewrite s cubed as s to some number plus 1. So this will become s to the 2 plus 1, so with 1 in the numerator. Right? So now that this exponent has the correct form of this one, n plus 1, but the numerator doesn't have the n squared, n factorial, because n should be 2. I don't have a 2 factorial yet. So I can't really go to this part directly. I don't have the same exact form yet. So what we're going to do is that we're going to take this fraction, we're going to add n factorial in the numerator, because that's what's missing. So this numerator needs n factorial. So we're just going to add to it. So we're going to multiply by n factorial there. If we multiply to the numerator, we have to multiply to the denominator. That way it's the same. So now this n factorial over, n factorial is 2 factorial. So now this 2 factorial over s to the 2 plus 1 is exactly this form. And I can take the inverse Laplace transformation out. But then I have this extra 2 factorial. What I'm going to do is I'm going to just leave it and put it aside. Don't worry about it. So now I have 2 factorial over s to the 2 plus 1 times 1 over 2 factorial, which is 1/2. That's what this fraction is equivalent of. And I can apply the inverse Laplace transformation. So I get inverse Laplace transformation of 1 over s cubed, which is inverse Laplace transformation of 2 factorial over s to the 2 plus 1. But with a half there, so I'm going to bring the half in front. And in this part, inverse Laplace transformation of this expression is exactly similar to this, so that will tell us it's going to be t squared. So that's going to be 1/2 t squared from there. Any questions? So a lot of times you're given at some point you reach a fraction, you kind of have to manipulate something out of it so that it's in the correct form, so you can find the inverse Laplace transformation. So that goes into this place, and now we can rewrite the final answer. It's going to be y of t is equal to 8 over 125 times half, and then the inverse Laplace of 1 over s minus 1/2, that's e to the 1/2 t, and then minus 4 over 125 e to the negative 2t, and then minus 2 over 25 t e to the negative 2t, and then minus 1/5 times 1/2 t squared e to the negative 2t. So it's not that straightforward. It should be easy, right? But some of the terms actually require a lot of work. And then obviously, you probably think, what if I just forget about doing it, right? If you forget to add a 2 factorial to use it directly to get t squared, then you're off by a factor. It's not too bad. At least you kind of recognize what function it is. But obviously, if we are solving some important problem or system with this, it's not going to be correct. Any questions? All right, the next one I have is the homework problem number 4. I just want to point a couple things out of there. So number 4, it asks you to solve this. So all the homework problems ask you to use Laplace transformation to solve the initial value problem. So we're going to solve y double prime plus y equals 3 sine square root of 2t with initial conditions. Y of 0 is 0. Y prime of 0 equals 5. So I'm not going to do the beginning work, so I'm going to leave you to it. So basically, you apply whatever we talk about so far in lectures and the recitations, and eventually you're going to reach this point to have capital Y of S is equal to 5s squared plus 2 plus 3 square root of 2 over s squared plus 1 s squared plus 2. And at this point, you want to find partial fractions. And at the end, again, I'm skipping more work here for you to, because this is your homework, right? So I want you to have the practice. So after you find partial fractions, you end up with 5 plus 3 square root of 3 in the numerator. Sorry, 3 square root of 2 in the numerator. Then we have s squared plus 1 in the denominator. That's one fraction. The second fraction is negative 3 root 2 over s squared plus 2 in the denominator. And the last step, the next step is finding the inverse Laplace transformation for each one of them. When I do that, I'm going to move the numerator to the side. So that will give me 5 plus 3 root 2. Oh, by the way, I want to point out that, I find those constants from my work. I could have made a mistake. So if you were doing your homework and then you, let's just say you didn't end up with what I have as the numerators, don't panic. Because chances that I probably have a mistake there. So you probably did the right work. Times inverse Laplace transform of 1 over s squared plus 1 minus 3 square root of 2 inverse Laplace transform of 1 over s squared plus 2. And then we have to figure out each one of them. So this is a good example because here we have s squared plus 1 in the denominator, so you can think about that's s squared plus k squared in the denominator. So the numerator we want it to be k or s, but we don't have s, we just have numbers, so we want the numerator to be k. The first one is relatively easy because we can just say, okay, k is 1. So we get k over s squared plus k squared. That's good. The second one looks like we're going to have to choose k to be square root of 2 because we have s squared plus 2. Right? So k squared is 2, k is negative, k is square root of 2. But the problem is that the numerator doesn't quite match that. The denominator looks good, but the numerator here, it needs a square root of 2 there. So what can we do? There's a couple of things we could do. We need a square root of 2, so we could multiply to the numerator and then multiply to the denominator, like we did in the previous example. So I'm just going to write here. So multiply by square root of 2, multiply by square root of 2. The one in the denominator we don't need, so we can move it in front of it. Eventually double cancel. So that's one way. The second way, in particular with this example, is that we already have a square root of 2 in front of it. We can actually just move it back into the inverse Laplace transform there. Because it doesn't matter whether it's in front of the notation or inside the notation, it doesn't change much. And then from there we should be able to finish it. Is that kind of helpful there? Is it okay if I just leave it for you to figure out the last step? Okay, I just want to give you I guess a hint without giving too much away for the problem. Any questions before we move on to number 5? Alright, number 5 here from the homework is we're going to solve this initial value problem, y double prime plus 2y prime plus 5y equals 1, with y of 0 equals 3, y prime of 0 equals 1. Again, I'm going to be a bit lazy not showing you all the work in the beginning. So if you do everything correct, at some point you're going to end up with capital Y of S equals 1 plus 7S divided by S times S squared plus 2S plus 5 So from here, obviously, there's not much we can do if we want to find the inverse Laplace transform. We're going to have to use partial fractions. So if we use partial fractions from here, and at some point, we're going to end up with 1 over 5 divided by S. You can move the 1 over 5 in front of the fraction, plus negative 1 over 5S, plus 33 over 5 divided by S squared plus 2S plus 5. And if we want to find the inverse of Laplace transform from here, the first one is easy. This 1 over S, we can look at the table, right? Figure out what it is. This one is a little bit difficult because the denominator is going to give us a lot of trouble here. So the denominator is not S, it's not S minus A, it's not S squared plus K squared. It's also not S minus A squared. Even if we try to complete the square, it's not going to give us exactly this. So if we don't have all of those, maybe we can have something S minus A squared plus K squared. It turns out that we can try to make it look like this last one by completing the square in the denominator. That's what we have to do. We need to complete the square for this denominator here. And in the numerator, we don't have to do anything. We're just going to leave the numerator the way it is. So the numerator leaves, so that's negative 1/5 S plus 33 over 5. If we complete the square in the denominator, we have S squared plus 2S. We need to add something to make a square. If you remember, it's going to add B over 2 squared. So B is 2, 2 over 2 is 1, 1 squared is 1. We need to add a 1. So basically we need a 1 there. The good thing that we get a 5, so we can pull a 1 from the 5. So the 5 becomes 1 plus 4. If we don't have a 5 there, we're just going to add 1 and a minus 1 at the same time. So this becomes negative 1/5 S plus 33 over 5 divided by S plus 1 squared plus 4. Sorry, squared. This is pretty good because the denominator now is S. This was S minus negative 1 squared plus K squared K2. So what do we do next? The next is that we want to replace S plus 1 with a new S. If we do that, the denominator, we have to do it to the numerator, but we don't have S plus 1 here, we only have an S. So what we need to do next is we need to convert this S into an S plus 1 to agree with the denominator. So this S here, we need S plus 1 there to agree with the S plus 1 in the denominator. So this, what we can do is we can just leave the negative 1/5. The S that we're going to write S plus 1 minus 1. That way the S becomes S plus 1 at some point when we separate the negative 1. So we need the s plus 1, this one we don't need, so we're going to move it outside of the parentheses. Plus 33 over 5 divided by s plus 1 squared plus 4. So that becomes negative 1 over 5 s plus 1 minus 1 over 5 times negative 1 plus 33 over 5, all divided by this denominator. And then simplify further, so that becomes negative 1 over 5 s plus 1. So plus 1/5 plus 33 over 5, so that's plus 34 over 5. And then s plus 1 squared plus 4. So there's two parts we did. One is we complete the square in the denominator. The second thing we did is we make the numerator agree with the denominator for the s part. And why do we do this? The reason we do it is that when we, at some point, when we apply the inverse transformation to this, we can actually replace the s plus 1 with the new s. So that becomes inverse Laplace transform of negative 1/5 of s, a new s, we use purple there, plus 34 over 5 divided by a new s squared plus 4. And this new s comes from s plus 1 in the previous part. And how is this going to help us? Well, it's going to help us because from here we can just focus on this part by separating the fraction into 2. But keep this in mind that this eventually will give us the exponential function, just like, so this part is going to give us e to the negative t at some point at the end, just like we have done before. So let me write down one more thing, then I'm going to stop. So this, if we want to find the Laplace transform of the inverse Laplace transform of this, so that will be inverse Laplace transform of, I'm bringing the negative 1/5 to the front, s over s squared plus 4. That should look pretty familiar to you. And then 34 over 5, inverse Laplace transform of 1 over s squared plus 4. And at the end, everything will be multiplied with e to the negative t. Before I let you go, I do want to point out one thing. This one is easy because that's just s over s squared plus k squared. But this one is not k over s squared plus k squared yet, so you have to do something with you to complete. And then you should be able to pick out each of the inverse. All right, any questions? Good luck on the homework, and let me know if you have any questions when you do those problems. I'll see you Tuesday.